Good morning. I am Prasobh and I am a PhD student at the Indian Institute of Science, Bangalore. Today we are going to discuss about millimeter wave MIMO channel estimation with 1-bit spatial Sigma-delta ADCs. This is a joint work with my PhD advisor, Sundeep. So, millimeter wave MIMO systems can provide cellular data rates of the order of gigabit per second, making them an attractive technology for next generation wireless communications. However, it is well known that the cosine power consumption of condensers will increase with an increase in resolution and sampling rate. Therefore, due to the large number of antennas and large sampling rate, using a higher resolution condenser for each antenna can be expensive, motivating the need to use low resolution condensers. Surprisingly, it turns out that reasonable performance can be achieved even with a very low resolution condensation of 1 bit. This means that 1-bit ADCs are interesting for millimeter wave MIMO systems because they can not only lead to a simpler design but also can lead to huge savings by reduced power consumption. Now, sigma-delta quantization is a classical technique used to increase effective resolution of condensers. Here, we will first sample the input signal at a rate that is higher than Nyquist rate, followed by condensing it with a low resolution condenser. Here, we have assumed a 1-bit condenser. Then, the difference between the input and output of this condenser, which we call as a condensation noise, is fed back in time to regulation architecture like this. The system will essentially act like an all-pass filter for the signal of interest and as a high-pass filter for the condensation noise. This means that this sigma delta condenser effectively shapes the condensation noise towards higher frequencies. In other words, for signals which are low pass in nature, the sigma delta condenser will effectively work as a high resolution condenser. However, a limitation of this approach is that in scenarios where the Nyquist itself is quite large, for example, like in millimeter wave MIMO systems, oversampling can be very expensive. This brings us to an interesting technique where the idea of sigma delta condensation is applied over the spatial domain than time. Here, we perform spatial oversampling by keeping antenna elements less than half wavelength apart, and we will perform spatial feedback by feeding back the condensation noise from each antenna to the next. This is an exact spatial analog of the temporal sigma-delta condensers that we have discussed, and such systems therefore essentially shapes the condensation noise towards higher spatial frequencies. Here, we illustrate the condensation noise for different angle of arrivals for a spatial sigma-delta condenser. We can see that for signals that are arriving from angles that are away from the array broadside, the condensation noise is more. In other words, the system will essentially act like a high resolution condenser for signals that are close to the array broadside. Here, we can note that these condensers Q are still operating at Nyquist frequency and the oversampling is happening only in the spatial domain. Therefore, for systems having large Nyquist rate, for example, like millimeter wave MIMO systems, spatial sigma-delta condenser is an attractive choice. Let us move to the system model. In this work, we will consider uniform linear arrays at both mobile station and base station with the NT and NR antennas respectively. At the mobile station, the input signal T is first quantized using a sigma-delta DAC before transmission using the RF circuitry. At the receiver, the received baseband signal X is quantized using a sigma-delta ADC to obtain Y. Due to the presence of extreme path loss at millimeter wave frequencies, we will adopt a line of sight channel model for the MIMO channel matrix. Here, alpha is the complex path gain, theta is the angle of arrival at the base station, phi is the angle of departure at the mobile station, and ABS and AMS are the array response vectors at base station and mobile station respectively, which are defined like this. Our aim is to estimate the MIMO channel by computing these parameters alpha, theta, and phi from the output of the sigma-delta ADC at the base station. The state-of-the-art technique in channel estimation in MIMO systems using spatial sigma-delta condenser is a LFMSE channel estimator, which is based on Buscagin decomposition and element-wise Buscagin decomposition. Buscagin decomposition essentially allows us to linearize any given nonlinearity which is subject to a Gaussian input. Here, to compute the Buscagin decomposition, we need to compute these matrices Cy and Cyx, which are defined like this. When X denotes the signal received at the base station, computing these covariance matrices essentially requires us to know the channel correlation, which is difficult to obtain in millimeter wave scenarios. Regarding channel estimation in regular 1-bit systems, there are plenty of techniques available. One such interesting and recent technique is the amplitude retrieval, where the authors propose to estimate both the missing amplitude and the unknown parametric channel in an alternating fashion. We will use this method to compare the performance of our proposed algorithm in the simulations. The main limitation in the prior art is that we need to know the channel correlation beforehand to compute the Buscagin decomposition Cx and Cxy. In the prior art, the authors considered a scenario where the user angles are assumed to lie in a continuous sector which is known beforehand. However, such channel models are more suited for sub-6 GHz scenarios and are not valid at millimeter wave. For millimeter wave MIMO channels which are sparse in the angular domain, knowing the channel correlation beforehand essentially aims at knowing the same angles which we want to estimate. Therefore, it is impractical. Therefore, it is not straightforward to extend the existing techniques which are based on Buscan decomposition to millimeter wave MIMO scenarios. Furthermore, the existing techniques are not capable of exploiting any structure in the channel and estimate the entire channel matrix as such, which contains NTNR unknowns, as opposed to 3 in our case. To avoid the need of channel correlation to compute Buscan decomposition and to exploit the parameter structure of millimeter channel model, we will begin by proposing a new noise modeling for spatial sigma-delta quantizer. Using the new noise model, we will then propose an angular channel estimation technique for millimeter wave MIMO systems. The operation of a quantizer is usually modeled as an addition of a noise term EI, which is assumed to be uniformly distributed and uncorrelated with the input of the quantizer RI. This assumption is true only in scenarios where the quantizer Q is having a large number of levels and the input RI is having a sufficiently large dynamic range. Therefore, for 1-bit quantizers, since we have only 2 levels, this classical assumption is not valid. A deterministic relation between EI and RI for a first-order 1-bit temporal sigma-delta quantizer is presented in this paper. We will now extend that result for a spatial sigma-delta quantizer. Here, we replace the quantization operation again as an addition of a noise term without any assumptions about the PDF. We can show that the relation between EI and RI for a spatial sigma-delta quantizer is given like this. Collecting such expressions for all NR antennas in a vector will give this. Here, we note that the nonlinearity was that of a 1-bit quantizer, where the traditional assumption that EI is uniform and uncorrelated is not true. However, using this modeling, we have expressed the operation of a sigma-delta quantizer using the floor function. We will now linearize the floor function by considering the floor function as an addition of another noise term. We note that the floor function is like a multi-level quantizer having a transfer function like this. Therefore, for scenarios where this term 1 by 2b URS plus half V1, when this term is having a sufficiently large dynamic range, we can indeed assume that the quantization noise arising from the floor function is uncorrelated with the input of the floor function. This means that for antennas that are away from the phase reference, the input of the floor function can be considered to be uncorrelated with the corresponding quantization noise Qi. Using this derivation, we can express the operation of spatial sigma-delta quantizer like this, where this is the effective noise term. For massive MIMO systems with a large number of antennas, this property is satisfied by most of the antennas. Therefore, we can assume that this property too is satisfied by all antennas without making much error. Hence, we can approximate the covariance matrix of this effective noise term to be 1 by 6 identity. Here, we would like to re-emphasize that this covariance matrix is not corresponding to the noise arising from the 1-bit quantizer. This is the covariance matrix corresponding to noise arising from the floor function, which we have derived here. We will now proceed to the channel estimation. For simplified channel estimation, we decide the pilot matrix S to be orthogonal. One way to choose that is to select the pilot matrix S to be G plus JG, where G is the Hardeman matrix. Here, we have assumed that the number of antennas NT is a power of 2. There are multiple ways to do this. The aim is to choose input T for the sigma-delta DAC at the mobile station to obtain this S. To do that, we can use the deterministic relation between the input and the output of a sigma-delta quantizer to obtain this expression. Using this expression, one way to choose this T is to select T like this. Let Y denote the signal received at the base station, where N is the effective noise term, which contains a Gaussian noise as well as the quantization noise. By assuming that the Gaussian noise and the quantization noise are uncorrelated with each other, we can compute the covariance of this overall noise term like this. Here we can readily see that the effective noise term is not spatially wide. Now to estimate these angles, we can use subspace-based methods like music. But since the quantization noise is not white, we begin by pre-whitening this receive signal Y like this. So we can pre-whiten the receive signal Y and we can remove the pilot like this to obtain a coarse estimate of the MIMO channel matrix here. Here we have a signal part and we have a noise part, where the noise part is both white because of pre-whitening and uncorrelated with the signal part. The SVD of H hat is given like this. Here, since the signal part and the noise part are uncorrelated, and because the noise part is white, we can see that the corner span of PS and the corner span of Rn minus of ABS theta are same. Similarly, the corner span of QS and the corner span of AMS phi are same. Making use of the orthogonality of the singular vectors, this means that Pn Hermitian Rn minus of ABS theta is 0. Similarly, Qn Hermitian AMS phi is 0. Here, we can find the angle of arrival and angle of departure by finding the peaks of music spectra given like this. Once we know the angle of arrival and angle of departure, we can easily estimate the path gain using least-square estimator, which is given like this. Before moving to simulations, we will explain a technique to set the voltage level at the base station. The voltage level B needs to be carefully selected to ensure good performance in Sigma-delta contexts. Here, throughout the derivation, we have assumed that the error due to clipping operation is minimum, and also that the input to the floor function is having a sufficiently high dynamic range so that we can assume that the input to the floor function and the quantization noise arising from the floor function, they are uncorrelated. Satisfying both these criteria at the same time is not possible because this will lead to conflicting requirements. Therefore, the optimal selection is difficult. So for this work, we will choose the voltage level in a suboptimal way as follows. We note that the input to the ith antenna at the base station is having a complex Gaussian distribution with the mean mu, which is given like this, and variance 1. If we assume that the path gains are having unit modulus, then the maximum value of this mu is given by root 2 PNT. We know that for a Gaussian random variable, the realizations are more likely to happen within a distance of plus or minus 3 sigma about its mean value. Therefore, by noting that the real part and imaginary part of this xi is having a variance of half, so if we choose the voltage level like this will ensure that the error due to clipping distortion is minimized for all possible values of mu. This choice is found to work well for line of sight channels. Extension to more complicated channel models are postponed for future work. Let us move to simulations. Here, we will consider setting with 8 antennas at the user, 128 antennas at the base station, and both user and base station are assumed to be uniform linearized with the lambda by its spacing, or with an oversampling ratio of 4. Here, we will illustrate the correlation between input and the quantization noise for a 1-bit quantizer and a sigma-delta quantizer. As we have discussed before, we can see that the correlation between input and the quantization noise for antenna indices away from the phase reference are 0 for the sigma-delta quantizer. Here, we present the normalized mean square error for channel estimation using different methods. UQ denotes the traditional unquantized MIMO system. AR is the state-of-the-art 1-bit channel estimation technique proposed here. And SD is the proposed channel estimation technique in MIMO system using spatial sigma-delta contexts. Here, the angle of arrival and angle of departure are assumed to lie in a sector of width 2 theta about 0 degrees. We can see that for scenarios where the angle of arrivals are close to the array broadside, the performance of the proposed scheme is comparable to that of unquantized MIMO systems and much better than that of state-of-the-art technique in 1-bit MIMO channel estimation. Here we have considered the angle of arrival and the angle of departure are lying in a sector minus 10 degree, 10 degree. In this case, we can see that there is a slight performance gap between the proposed method and unquantized systems, especially at large SNR. This is inevitable due to the presence of larger quantization noise at angles that are away from the broadside and also the larger quantization noise at higher SNRs. In any case, even for scenarios where the angle of arrival and departure are assumed to lie in a wide sector of minus 30 degree, 30 degree, the performance of the proposed scheme is much better than that of traditional 1-bit channel estimation techniques. This clearly illustrates the advantage of using spatial sigma-delta quantizers over regular 1-bit quantizers for millimeter wave MIMO systems. To conclude, in this work, we have proposed an angular channel estimation algorithm for line of sight millimeter wave single-user MIMO systems. To avoid the requirement for knowing channel correlation to compute Buscan decomposition, we have presented a new noise model where the operation of the sigma-delta quantizer is expressed using floor function. While we note that the IID assumption is not true for 1-bit quantizers, we can consider the floor function to be a multi-level quantizer, and then we can apply the traditional method of noise modeling to realize a equivalent noise model for the spatial sigma-delta quantizer. We have found that the input and quantization noise are uncorrelated for antennas that are away from phase reference. Using this new noise model, we propose a channel estimation technique which does not require the prior knowledge of channel correlation. The proposed technique is found to significantly outperform conventional MIMO channel estimation techniques like amplitude retrieval, and the performance is also comparable to that of unquantized MIMO systems, especially at the lower SNRs and when the angles are arriving close to array broadside. This concludes the presentation. Thank you.